Hello everyone, thank you for watching this video. In this video here, we are going to talk about three components related to using MATLAB for programming. The first part is about what is MATLAB and what MATLAB can do. The second part is about the basic usage of MATLAB, including some simple syntax, using script, debugging, and plotting, and finally an example. The last part of the video here is about how to use straightforward way to make your code lasting for long. Let's start with the first part. So MATLAB is short for Matrix Laboratory, and as the name says, it is good for calculating number matrices. And the advantage of MATLAB is that the script is very readable. Script is a set of commands that you ask computer to execute. Readable means that when you look at the script, you can almost understand the action computer will do after the execution. So it's pretty much like English. The second part is that it has a very powerful library for calculations. Library here means a database of codes or functions. For example, exponential, divide, spline interpolation, and even some of the more complicated plotting tools here. The third part is that the plot function is easy and nice. I think most of you have already used Excel to plot data, so the process is pretty straightforward, where you just drag down a button to plot it out. But different from the Excel function, MATLAB uses script to do the plotting. It seems to be hard at the very beginning, but once you get used to it, you will find it's very convenient. There are several things that MATLAB can do, but Excel cannot do. For example, if you have a spreadsheet with multiple tabs and you want to plot all the values within A1 in different sheets, then you find that Excel is very clumsy to do so. But in MATLAB, it's pretty straightforward. The second thing is that if you come up with some line of data you want to plot, but instead of plotting every single point, you want to plot every third one, and that's not very easy. But in MATLAB, it's just one sentence. It's just a Venn symbol to be able to do so. The third part is also quite obvious. It's about like contour plotting or even 3D analysis. So those are basically not the battlefield for Excel, but very much so for MATLAB. So this is the advantage of it. Anyway, we've already given a quick idea about what MATLAB can do. So now it's basically to look at the interface and then how you're going to use it. So if you look at the screen in front of you, you've got the default interface for MATLAB. So right in the middle, you've got the command window. So if that's being activated, you got the two greater than symbol plus a flashing command prompt. That's where you're going to communicate with MATLAB. The window on the left-hand side has got the current folder. So this is basically what are the existing files within your working folder. So your working folder is actually being displayed in the horizontal bar right in the middle. So you can click here to tell the address as specified here. You can move it simply by dropping down bar to different folder, which will actually show what is inside that folder. Or you could use some of the commands here. So that's when you run some simulations down there and save the files, those files will be saved in the working folder. So you always need to know where your working folder is. The second key point here is that if you try to put your working folder in a remote drive, that may make the simulation relatively slow, because the writing or reading from the remote drive will be much slower as compared to working in a local drive. So the remote drive also includes USB. So if you really want to do a very heavy calculation, the best way is to use local drive, and after completing it, you can copy the files down to your remote drive or even USB. So that is preferred. The one at the very bottom is the workspace. Workspace basically lists all the variables and also the values of that variable. On the right hand side, I have a pop-out window. So that's editor. So that's basically command editor we normally use to store a bunch of commands that needs to be run at the same time. So normally I dock this one out. You could dock it back in like this way, and that ends up with different layout, but it gives very small space for command window. So I normally just dock it out. So in case if you can't find some of the things, say this one is disappeared, this is disappeared, what you could do is that you just simply click layout and default. That will go back to the normal stage. So again, I'll undock this and then put in next to the editor here. In the following part, what I'm going to do is to go through all the commands listed in this file here. And this file will also be downloadable from a link below. So the way of communicating with MATLAB is to put in the command into the command prompt, and you will see the feedback. So let's try the first one, pwd. So after putting in this command, you will see it returns ans is equal to C and a string. And this string is exactly where your current directory is located, which can be seen by the bar here. The other thing is that once you have run this command, you will see that a variable called ans is created, and that comes with the value of where your current folder is located. Basically, ans is a variable that always stores the latest result from your input. So let's say we could go further down to the second command, ls, and that ends up with all the files that is listed in the current directory. So the dot here means current folder. The two dots here means the parent folder, and the other one is untitled2.m, which is the existing files inside the folder. If you know a command, but you don't know how to use it, the way of getting better idea is using help. So help pwd, and that tells you that pwd show and print the current working directory. We use help a lot. I can tell you that a lot of commands I can basically memorize the way of using it, but in a lot of other cases you don't really know how to use this command, even you know what the command could do. So in this way, you can basically use help, or you try to use Google to put in the command, and then a page will tell you for a lot of examples. So you're always trying to learn something based on the project that you've been working on. The other way basically help is that you try to find out the right command that is able to solve your problem, which we'll discuss later on. We'll do some simple algebra calculations. So 3 minus 5, after executing that, you will see that the ans has been changed to -2. Also, the value has been displayed at the command prompt. We could also do trigonometric calculations here. So 2 times 3.14 ends up with 1, and that is also being stored in the workspace. If you want to give a value to a variable, what you could do is to say, for example, a is equal to 3 minus 5. So 3 minus 5 is equal to -2, and the -2 will be stored in the variable a. That's expected here. -2 is displayed here. The value is also shown in the workspace here. The other thing is that we could use a cosine 2 times pi. Instead of using 3.14, which is the approximate of pi, the pi here is the accurate value of the pi here. So we could enter, and then that ends up exactly like 1. After we got A and B, we could use the calculation just by variables. So say A minus B, so that ends up with -3, and -3 is updated to the ANS file here. We could also store the outcome to another variable. So in this instance, it is C. And that means we will do the A minus B here and then store the result, which is -3, down to the variable C. So that's also expected result here. Now let's look at the one below here. So A is equal to A minus B. That's -3. So if we just simply look at the command, then the A on both sides of the equal symbol is going to be cancelled out, and then B is basically 0. Is that the way how the command is being executed? Apparently not, because the outcome is actually A equal to 3. And why that could happen? The reason it happened was because originally A was -2, B was 1, so A minus B is -3. And the -3 is going to be assigned to the A that replaced the original value, which is -2. So that's basically how this command interpreted. So the second one here is, say, D minus B. When you do that, you'll find that D is not declared, and that ends up with an error. So once you use variable, you have to use the variable that is well defined. So as you can see that every single time we run a command here, there will be some outcome pop out from the command window. And maybe those information are not quite necessary because it will be stored in the variables we assign anyway. So can we actually suppress the outcome from the command window so that it is less verbose? You can do that. The way of doing it is to put a semicolon at the end of the syntax. So currently A is equal to -3, B is 1, so the outcome is -4, and that -4 will be assigned to the ANS value. So if we run this, you will see that -4 is being assigned, and yet we didn't see anything immediately after this command being executed, and this is exactly what we want. So in most of the calculations, we don't literally need to check every single line outcome. So we could always put a semicolon at the end of each line, so the calculation wouldn't be so verbose, and you can always check the result directly from the variables. Now we can define another one. D is equal to 0.6, and that ends up with D is equal to 0.6. So basically the integer part, the 0 could be ignored, and still the system understands what you're talking about. So the following command here is talking about how the operators has been executed in the sequence. So this command here is not quite human readable, and we don't know what is the priority of how each operator is going to be executed. So there are several possibilities as we show in the slide. In all of these options here, basically there is no difference about where the B and E is located. It's mainly about the one right in the middle. One of the options here is to say that B and A are the exponent, and this section in the group is in the numerator. And the second option here says that basically the whole thing underneath is in denominator. And third option here says that this section here is in the denominator, and yet the rest of them are in the numerator. So the final one says that only you've got the b in the denominator, and the rest of them are all above in the numerators on top. So which is your option? So the basic way is to look at the sequence of how computer execute the operators, which follows BEDMAS. So it's bracket, exponent, division, multiplication, add, and subtraction. So if we do that, we know that once the computer has received the command, they will do the exponent first. That's the number one, right? The second one is C divided by B, right? And then it's about the multiplication. I think if you do this, the result looks very clear, and then the right solution here actually. So the D, C, A power B and A are all in the numerator, and the B underneath, the B here only in the denominator. We always need to follow the BEDMAS. There is another issue that I have come across quite often, which is the fact that there are so many brackets in the syntax, and that really makes the sentence not understandable. So there could be a case where you have 3 to 4 brackets, and then it's very difficult to find out which bracket is associated with what the other one. So that actually makes the command not quite understandable. So my advice on this is that you really try to follow the BEDMAS. You can clearly reduce the number of brackets in this system. So in my case, if I want to really make this one relatively human readable, the way that I'll do is to put everything in the numerator on top and put the things in the denominator at the very bottom. So if you look at the sentence like this, you basically can arrange the whole equation into a human readable way by heart, and that will make yourself free of bugs. And a lot of time, if this is not done very well, it could be potentially have the bugs, and then you don't know how to solve the bugs. So always try to make your command neat so that you can just use your eyes to read about what is the equation you're trying to describe here. Right, that's basically about the operations. The next one we are going to describe is about arrays and matrices. So A, if we double click it, it will end up with a variable here, and that's pretty much like a spreadsheet. So you will see that the -3 is stored at the first row and first column. And if you want to see the dimension of A, you could use a function size A here that ends up with 1 and 1. This actually tells the dimension of A is 1 row and 1 column. And to make an array, what we could do is we put in every single value to the cells in C. And by doing this, we create an array. And this array has got 1 row, 4 columns. And we can do the simple calculations by addressing each location here. So C11 is equal to C11 here is 1. C22 here, well, C22 doesn't have anything. So if we basically run this line, then it will give error. But if we try to change it to C12, that actually comes with a value. But of course, because C11 is 1, so it doesn't change 2 here. So basically by running this, we end up with an array, but it's in a row. We could also look at a simple way to make a matrix, which is to use this line here to create a C. So this C here has got again 1 row, 4 columns. And if you have got the semicolon to separate those numbers, that result looks slightly different as compared to the one we did before, because we end up with 4 rows and 1 column. The other way basically we can do is interactive input. So we need to type. So E is equal to bracket 4, enter. What you will see is that the MATLAB tells that it is waiting for input from the command window. So we can keep adding 5, 6, 7, right bracket, and a semicolon. And that finished the whole syntax input. So we end up with 5, 5, 6, 7 in a column rather than in a row. To access every single cell in the variable, we could use this command here. So that tells you it's the first row, the third column, which is actually 6. And same thing about D here. So D is 4 row, 1 column. So if we run this command, that will end up with the number 4 here, right? But if you do the other way around, it wouldn't give you the results because it doesn't have data in at that point. We are going to do some matrix manipulations. So the first thing we're gonna go is C times A. So we know that C is a row and A is a scalar, which is a single value. So if C times A, the result is going to be that -3 here will be multiplied by every single element within the C, right? So basically the first one will be -6, the second one is -12, and so on. So that's the expected result, right? So -6, -12, which is expected. Now we try A times D here. So A is a scalar and D is a vector, but in a column. So it's 4 row, 1 column. And if you look at the result, that again ends up with a column, and the calculation is done by the value in the scalar multiplied by every single cell within the D, right? So -3 times 1 is -3. -3 times 2 is -6, and so on. The next one we have here is D times C. So we know that D is a column and C is a row. So if we do that, so let's look at this. That's the example. So if D is a column and C is a row, we basically are following this format. And to make it possible, what we need to follow is that the inner index for these two array needs to be exactly the same. So in this case, it's actually 1. And the outcome is going to be the external indices of the two array, which is going to be 4 times 4. And the value here is going to be A times E, A times F, A times G, A times H at the first row. So that's basically the formula to do so. So we can run it and see what happens. That's exactly the way we end up with a matrix. Now the next one, C times D. So C from here is a row and D is a column. And in that case, the inner indices of the two neighboring array is the same, which means this execution is doable. and the outcome is going to be the external indices, which is 1 times 1, right? That's how we get this. And the calculation will be done by A times A plus B times B times C times C plus D times D. And we can look at that. We end up with a single value, a scalar, as the answer. Can we try D times D? So D is a column, which is 4 row 1 column, times D, which is the same size. Is this doable? No, it doesn't. So the inner index of the two neighboring arrays are not the same, and that's not doable. But now, if we put apostrophe, we end up with a value. And how that is possible? Then we need to understand what the D apostrophe is doing here. So if we look at D, basically it is a column, but the D apostrophe converts the column into a row. Basically, it transposes the D in the front. So if we transpose the first D in the front, then we basically follow that formula, and that formula will end up with a scalar in the end, which is the reason. Now, the second one here, is this doable? D dot time D. Let's just try to run it here. It does end up with values. Why is that? So the dot multiplication here is to do the calculation in a cell by cell manner. So if you look at the D, it's basically 1, 2, 3, and 4. So if everything is run in a cell by cell manner, the outcome will be having the same dimension as compared to the original one, and the value is going to be 1 times 1 is equal to 1, 2 times 2 is equal to 4, 3 times 3 is equal to 9, and 4 times 4 is equal to 16. So that's basically the dot product we were talking about, and this has been used quite often in MATLAB. And the same thing applies to D dot divide E. So here the D and E are all columns as specified by the semicolon here, and dot divide E is again a division in the cell by cell manner. The following two commands is about the division of the vectors, which is a little bit difficult to understand. D divided by E, so when you look at the D and E, and the D and E are exactly the same shape, but they are dividable. And why that is able to end up an outcome like this, it is simply because that the D divided E by E is basically a reversed operation of D is equal to ANS times E. If you do the D divided by E here, it ends up with the answer here, right? So what we can try here is that if we use ANS times E here, we would be able to get exactly D here, which is 1, 2, 3, 4 in the column, right? So that's basically what D divided by E is doing. The one immediately below here is D backslash E. That ends up with a value here. It basically calculates the outcome of AX is equal to B. So let's say in our case here, it is actually dx is equal to E, right? So we know that if D is a vector and E is also a vector in the same shape, the x here is going to be a scalar. And this scalar is a bit magic that it makes the dx as close as possible to E. So we could simply try to multiply this variable, the scalar, which is equivalent to nsx here, by the D. And you find that it's actually quite close to E, so we can try that. So that's going to be D times ANS. And if we compare this to E, it is 5, 5, 6, 7. And this is actually the closest approximation we can get. So that's the \E. And this is not a very common operator anyway, but you see the best way to get more details is to basically search MATLAB \operator, and that will give you a bit more details. Now let's look at matrices. So by copy the command below, you will end up with a 4 times 4 matrix. And you could also look at the size of the E, which is going to be 4 and 4. And we could also access a cell within the matrix, E34. So the third row and fourth column, that's going to be number 5, isn't it? Expected? If we do this, E0 here, it tells you nothing. But if we do E1, and that tells the result is 1, which is literally that. And if we do E2, and that's number 9, which is actually the second row and first column cell data. So how could that possibly be happening? Even we've got a matrix, but in the computer memory, the matrix is stored in a linear fashion, and the storage is down in the row as a priority, and then go to the second column, the third column, and fourth column. So what's the indication of this? 2 things. Number 1 is that MATLAB is based on 1, so the base value of a matrix index is going to start from 1 rather than 0. There are some differences. Let's say Python starts with 0 rather than 1. C++ starts with 0 as well. VB starts with 1, so different programming language has different ways of starting the indexes. The second key thing here is that how the matrix is being stitched into the memory. So the indication for doing this is that if you want to do a sweeping of all the variables in the matrix, it's always suggested to do in the row as a priority, then the column. Because by doing so, the memory access is always next to each other. That makes your speed much faster as compared to you do 1, 2, 7, and 8, which is literally stitch back and forth, that actually slow down your program. But in these days, it's relatively not subtle, but it's always good to know how internally the system works. And we could also use one interesting thing. We say END. And END is basically to look at the very last cell in E. So in this case, it's going to be this one here. That's 3, right? The other thing we can do is basically look at a section of E. So if we run this, so 1 here is basically the index for rows, and 1, 2, 4 is the index for the columns. So if we look at the result, it is basically returning the first row. And how is that possibly happen? To understand it better, we can just simply do 1 column 4, and that's actually 1, 2, 3, 4. So this command here is basically equivalent to this, and that things needs to be in the bracket. See, that's basically ends up with the same thing as we separate the 1, 2, 3, and 4. So this way is quite straightforward to access the first row. And you could also do the same thing for the columns. So that line here only accesses the very first column of the matrix. This command here is a little bit tricky. So that basically accesses the second row and third row, and within the second row and third row, they just focus on the first, second, and third column, which is this and this. right? So that's the reason why you end up with 9, 3, 1, 4, 6, and 8. There's another interesting symbol that you could use. That is column, comma, 1. The 1 here tells you that it's actually the first column. And the column here is to tell that look at all the data here. So basically that returns all the data in the first column. And if we rerun that, that's basically expected. We could also do this to be able to understand this specific command. I think it's better to look at what that will come up with. 1, 2, sorry, 1, column 2, column 4. So that actually ends up with 1 and 3. So how that possibly be happening? So before we understand that better, so we can go back to this. So the 1, column 4 basically means starting from 1 up to 4 inclusive with an incremental of 1. So if we do so, then we basically go to 1, 2, 3, and 4. Now if we add a 2 right here, right in the middle, then that means you're starting from 1 and finish at 4 inclusive with a step of 2. So every time they add 2 on top of the previous value. So the first value out of this is obviously 1. The second is going to be 1 plus 2. That is going to be 3. And 3 is less than 4, so that is also included. But if we increase 3 by 2, it is equal to 5, and 5 has gone beyond 4, which is not within the range that we are talking about. So basically running this command will end up with 1 and 3. So go back to the story here. So if this one is equivalent to 1 and 3, we are expecting these two are exactly the same, and we can see that the command end up with the first row and third row. So that's 1 and 4, and that's how it works. The other interesting thing that you can work with is that you can look at a mask matrix. So we simply say E is greater than 2. And let's look at the result. So it ends up with a matrix. And the matrix is a binary one. They basically put 1 to the location where the value is greater than 2. Right? And then you could hatch them. So we end up with a line of the results. And how possibly the line would happen. Remember that this mask matrix, we call it mask matrix, is also being organized in the row prioritized manner. So if we put in this mask matrix as the index for E, they will disable the first value, enable the second value as the first output, enable the third value as the second output. So if we go back to here, you will see that this value must be 9, and that's the case. And the second value is going to be 4, and that's also the case. The third value 1 here is disabled, and that's not shown here. And the number 4 here is the third value according to this line. So basically, by doing this, this command tells you that first find out all the values that are greater than 2, and then display it in a column prioritized sequence. Basically, that's the command, how it works. The other thing, the one below here, we've got E bracket, E double equal is equal to 11. Wow, this is a lot of story here. So to understand this one a little bit better, we first need to understand what is E double equal. So double equal here is not an assignment. The assignment is basically to give a value 2. So let's say A is equal to 2. That means you assign the number 2, the 2, into the variable called A. But this double sign here is not an assignment. It basically checks whether this is true or not. So let's say if 2 double equal to 2, this check is going to be true, which ends up with 1. Whereas if we are putting 1 double equal to, and that's not true, so that will end up with a 0, which is false. So go back to the matrix. So E double equal to here is going to check whether every single cell, any of the value is exactly equal to 2. And in our case here, none of them is equal to 2, right? So that's the reason why it ends up with all zeros. But instead, if we try to change the E is equal to 1, E double equal to 1, then we're expecting this point being equal to 1 in the mask matrix. So we can do that. And as you can see, all the cells that has the 1 value has been singled out as the mask matrix here. Once we do the checking, you will see that the values inside E is not being changed. It's not assignment. It's basically to check whether this value has satisfied some conditions or not. Basically, after adding this mask matrix, the basic way of understanding mask matrix is basically like you wear a mask to remain your nose and eyes visible, and the rest of the face is not visible. So the mask matrix here is also the same case. So if you put the mask in here, it only shows the values that are at these points, right? Go back to the command here. What does it say is that find out in the matrix E any cells that has got the value of 1 and change that value from 1 to 11. If we do so, you will find that all the values that is equal to 1 has been changed to 11. Okay, so the very last one, the end here, is basically to look at the very end of that dimension. So E is the 2-dimension value. So look at the last row and last column. Now we do simple matrix manipulations. So E times A, that ends up with a matrix because A is a scalar. E times C, and that didn't work because the E is 4 times 4 and C is actually 1 times 4. So the index, the inner index, doesn't match up together, which is the reason why it didn't work. And about E apostrophe, it's basically the transpose. The original E is this, and if we look at the E apostrophe, it basically transposed the E. Now let's move to using squeeze to look at a 3D matrix. As we discussed before, that when you use a 2D matrix and then use the mask matrix to show only part of the matrix, it still maintain the original part of the matrix. Let's call this one A here as 1, 2, 3, 4. So A, the very first column, is still the very first column will still return the result that shows the very first column in the column-wise way. Whereas if you have A1, the first row, and then the results still look like in a row manner. And the same thing applies to the 3D matrices as well. So if we try to use this script here, the first one is to provide a 2D matrix in the first tab, which is the 3D dimension. And the third one is to provide a 2D matrix for the second tab. The reason I call it tab is because that it's more or less like a tab in spreadsheet. Every single tab represents a sheet within the Excel workbook. So that actually produces a 3D matrices. So the first dimension could be accessed by this one here. So it's 1, 2, 3, 4 in 2 times 2 matrix. And the second one is can be accessed by the number 2 at the third index to show the second matrix. Now let's think about if we want to get to the first row, first column of every spreadsheet. As expected, the result will look exactly in the same format as we did before. So that means the column here, it will end up with actually 2 answers. The first answer is the answer from the first spreadsheet. And the second answer, the number 5, is actually from the second spreadsheet or the second tab. So once you end up with 2 results, it becomes very difficult to do any manipulations. Let's say, can we do this? It becomes a little bit tricky because you actually have to deal with multiple results, and you couldn't actually give this value to a single B, let's call. It's not that straightforward. So what we usually do is basically squeeze them into a row-based array or a column-based array, and that's basically the squeeze is able to work for us. So if we squeeze that, let's say C is equal to squeeze the result, you will see that the result becomes 1 column, which is basically the preferred way how MATLAB stores all the values. So that's basically to look at the 3D dimension. As you can see now, if I ask everyone to plot the data of the first column and first row over different tabs or spreadsheets, it's very straightforward in MATLAB actually. We'll move down to using the script workbook. As you can see now, all the input we've done before is using the command prompt. So basically we need to interact with MATLAB very often to be able to put into the command that we want MATLAB to use. But this could be clumsy because if we have 1,000 lines of code to be executed, how can you put in 1,000 lines just one by one? That's not possible. And the best way of doing so is to use a script editor, which MATLAB provides. So the way to open up a new script editor is to click the button New Script at the top left of the window. When you click that, you will see it provides a new blank line, editor line, for you to edit something. The reason that this is on is because I actually have a list of scripts showing here. So if you don't have that, once you click that button, the editor window will pop out. Let's copy and paste this bunch of code inside our new script file. So we paste it, and after pasting it, you will see that the name immediately after has got a star here. The star basically says that this file is not being saved. So you have to save it properly. So the way of saving properly is to click Save, right? So they will show something like this. So the working directory is the current directory, and then the file name is this. So let's say this one, we call it test.m. right? There's something important to trying to avoid when you try to name a script file. You try to avoid of using space, minus, a slash or backslash. And the reason is because that in some cases, particularly in the old MATLAB versions, the system will consider a negative, like a minus symbol, as a variable a minus a variable b. And that actually happens very funny because you tend to put into a file name, but turns out they do an algebra calculation. And the same thing applies to the space here. So usually the space in string is being represented by backslash and space rather than just a space. So you will create some kind of funny thing. But I think later on MATLAB solved that problem. But as a good test, or let's say you try to write a script that is compatible to all the MATLAB versions, it's better to avoid using space, minus, slash or backslash. And the best way of to separate the name strings are basically use underscore. That's what I prefer to use. So now we save it, and you will see that the star here is not there anymore. Once you have this file, you can run them by simply click one button. So let's do that by, let's just give a little bit space. So that's the run here. So the run here will run all the command within this script. So we can click that button, and then what happens is that it tells you an error. And if you read carefully, they will even tell you the details of the error. That is because that the dimension of D and E cannot do a multiplication because it doesn't follow the rule. And the best way, if you want to make sure D and E is exactly the same, we have to use dot multiplication, which means that the shape of D and E is exactly the same. And also the other interesting thing is that they tell you where the error comes from. So if you click the number 11 given here, they tell you that, look, this is exactly where the problem happens. All the lines immediately above the line where the error comes from has been properly executed. Because when you look at, say, HG in your workspace, you will find that the value 9 has been given. And if you look at the D times E, D is actually a column, where E is a matrix. Okay, so a column times a matrix. The inner index between the two is not the same. And of course, they wouldn't be able to do the calculations. If we want to fix the problem, reverse the sequence of E and D, we can change that to D times, say E times D, and the problem will be solved for sure. Now, there's some other useful thing that you could do when you use script. The script can tell you which line is being running incorrectly. What if you really want to see all the details? What you can do here is basically going through a debug process. And the debug process could be enabled simply by clicking your mouse at the dash immediately after the number 9s. So if I click a button here, you will see that a red dot appears. So what the red dot here do is that when you run the script again, all the lines immediately above the red dot will be executed, whereas the line immediately after the red dot will not be executed. Right? Let's try to do another one here. So this one could be somewhere here, right? And then we click the run command. So once we click the button, you will see the first line, which is to clear all, has been executed because there is nothing inside our workspace. Whereas the current line, which is the definition of E as a matrix, that has not been executed at all. So what if I want just to run everything line by one line by one line? We can use another command called step. So if we run that, you will see that E has been defined because this line, the lines immediately above the green arrows are all being executed, where this line is about to execute if we click the step. So if we click it again, you find that D is executed. And the other time that if you just don't want to click so many times of the steps, what you could do is to click a button here, somewhere away from the arrow, and then use the continue. So the continue basically says keep running until you see the next breakpoint. So if we do so, that will move immediately from the number 7 to number 11, where the problem comes. So currently, all the lines immediately above this green arrow has been executed, but the one after is about to execute it. So the same problem come again. So even at this stage, we can try to run that. And you will see that the same error comes. And the only way to resolve that issue is to change the sequence of D and E. But at this stage, the new command will not be updated by itself. You really have to click the save button, and then you can repeat the program by using the new methods. But nevertheless, you find out the error and then you can keep it going. So as you can see, so if we run the H is equal to E times D, it runs properly. And then the program completes. Basically, this is the way how you can use the MATLAB script. And for all the project, we're basically trying to use the base commands in MATLAB to solve a specific problem or complete a task. So always use a script and save it properly to make sure all the work you've done before is being properly saved. And the other good idea is that rather than just save to one file, once you reach a milestone, you can always save to another file. So if this file, by some reason, being damaged, you can always come back to use the previous file. So that's actually a good habit you can develop from now on. Let's move on to the next. So the next one here is about to save the environment. So we'll be focusing on that, and these two will be revisited later. So it's about the logical expressions. Now we always see that the script file can be properly saved. But how about the environment? Let's say instead of saving this bunch of things, we want to save this so that later on we can access the result. We can analyze the result further up rather than just running all the script. Yes, you can do that. The way of doing that is to use the command here, save a.mat. So after running this command, you will create a file called a.mat in your current folder. And later on, you just need to click that file to be able to return all the values you stored in the past. So once you do that, you will find that a.mat is there already for you. And once you save that, you can clear your workspace. So now it's cleared. If you want to go back, that's pretty straightforward, and you can just simply do that. It comes back to the previous stage. Now think about this case. So for the previous project, we worked with water boiling experiments with different initial mass or different heat conductance and those parameters. And if you use MATLAB, you obviously can do the same thing for numerical models. But this numerical model will end up with different scripting file. And the scripting file will save to different workspaces. So each workspace will have the same thing, but they are in different environments. So how can we lump everything all together? The way how we can do it is basically save it into the whole environment into MAT file, but load it into a variable. So if we load a.mat into st, what happens is that a st file as a struct will be created, and inside the struct it has exactly the same environment as we did before. So if you want to get the one of the simulation result within the a.mat, you could say st.a. So that actually visits the a variable within the st struct. So imagine now if we have another simulation results, and that could be called b.mat, then you could say st2 is equal to load a2 b.mat, because currently I do not have a.mat, b.mat, so I have to use the a.mat here. Just for example, let's say now I've got st2, and the st2 here is a different simulation. But if you do so, So if we put it in here, then you will see you've got st1 and st2, and both of them has got a, and these two are the same is simply because the a.mat file is exactly the same. So by doing this, you could always compare the result from different simulation attempts and try to plot the result if you need. So that's a very useful thing, which is to use struct and also save the simulation result to a local file. And of course, you could also always try to double click the file, copy and paste this bit, and then save it to a spreadsheet. Now let's move to the next part, which is to understand the if statement. So as suggested, we copy the following part into a new script file. So new file, copy and paste and save it. So when you save it, we always use check if condition underscore to separate the words, and after that it's ready to go. Now if you look at the script, instead of every single line starting from the first, some of the line comes with indent, and the indentation level is different. What does it mean? The indentation is actually an indicator of that indented lines are subordinate to the lines above. So the lines that is at the very beginning has the highest hierarchy, which is such a big one. So if, else if, else if, else, and end. That's the highest level. And then they will first check which condition does the argument satisfies. If either of this, for say, if this line satisfied, and the line that is subordinate to that if condition will be executed, and in that case, none of these lines will be executed, and vice versa. So if that condition here is being satisfied in the first place, then these lines will not be executed. So once you do the if condition, the most important thing is that all the condition needs to be mutually exclusive. You can't really have a condition that both arguments satisfies. And if that's the case, whoever is being executed first will get the chance to run. So if, let's say, if this if is the same as the if here, so this bit will run, but the rest of them wouldn't. So you always need to take care of your if condition very carefully. Make sure that there is no conflicting in between those if conditions. The second thing that we will discuss a bit is the logical operator, which is here. So let's say if we remove this part, everything makes sense, because the if condition is to check whether index 1 is greater than 0. But if we add this double and index 1 is less than 3, what does it mean? This logical operator is called AND. So this if basically says that if index 1 is greater than 0 and less than 3, so basically if the index is between 0 and 3, run this bit of commands. And again, we've got the double equal. Remember, double equal is actually a condition check, not rather assign values to that, right? So we find a bug here. It's instead of index 1, we actually, instead of index, we have to use index 1, but that will come out when we run the program anyway. The last line here, they have a very special operator here. So they say that index 1 is less than -8, double vertical lines, and the index 1 is greater than 3, greater or equal than 3. So what does this mean? This is all actually. So either index 1 is less than -8 or index 1 is greater than 3, run this bit of lines. And still, if we look at all the conditions, there is still quite a bit things that's not being defined, which is that when index is between -8 and 0. So less than -0 is here, and in between it's not defined, but from 0, 0 to 3, is being well defined, and the 0 is being defined, and greater than 3 is being defined. So what happens if there is something in between, which is between -8 and 0? It basically goes to else. That means if none of the condition being given satisfied, just come down here. So let's run this script. So we find that -1 basically falls within else. So what we expect is that a is equal to 3 will be executed, and then let's give it a try. So to do that, we can basically run by debugging state. So now the command immediately above has been executed, but the one below has not been executed. Then we click that button and then check in the very first one. Even before we do that, we can try to copy and paste this bit in and see what happens. You see logical is 0, which means that this condition is not satisfied. And you can see that rather than running down to here, it immediately dropped to this line, because the subordinate script is not going to be executed if the condition here is not satisfied. So the second condition obviously is not satisfied, they will jump. But this time when you jump it, they say that index is not defined, and that was the error we identified in the first place. So we need to change it. So run it again. And then once you go again to the index, the double equals 0 as the checking conditions, you will find it's not executed. And this line will not be executed either, because it's not, the logical condition is not true. And else, it basically is where that one goes, and then a basically ends up with ends up with 3. So next time what we can do is that we try to put it into a 8, right? So 8, and 8 actually satisfy this line here. So when we run that, we'll find that a is equal to 10. So let's do that. So we quit debugging first and then run it again. And we could also remove the red dot here to make sure that it doesn't block the way. So we just need to check the result. So the expected value is that when we run the program again, a is equal to 0 after it's completed. A is equal to 10, sorry, 10, and that's actually the case. The other interesting thing is that we could do a nested if condition. So once we got the if condition in here, in this bit, we could have another if condition inside. But this if condition has nothing to do with the external if condition at all. So they can only be executed when this condition has satisfied. We can try that. The way we can try it is to put a index 1 that satisfies the argument here. So let's say if this is number, sorry, that's basically between 0 and 3. So we basically need to put number 2 here. So we run it again and then do that. And now this bit can only be executed when a is greater than 5. But because we just defined a is equal to 2 in a few lines above, this d is equal to 7 will not be executed. And that's actually the case, because the the green arrow immediately go down to the bottom of the script. So this is about if condition. If condition is very useful to navigate the simulation or the script flow based on the condition you want to satisfy. And here is a good example. If you always got a bit subordinate script, making sure that the indentation is being given so that your code is well structured, that will be easily understand later on if you revisit your code. Let's move to the next problem. So that's basically to understand further about the if conditions. So as you can see, this if condition here, the index 1, the argument, is only a scalar. Can we do vectors? Not really. We can try that now. So we define here E and D and C. And now what we try to do here is that, remember, this is AND. So basically what we try to achieve is that if E is in between 5 and 7, change the value to 6.5. Can we do that? Let's give it a try. It doesn't say that, because that these operators can only do things when they are the scalar values. So what if we want to do that? We actually have to use for loops to solve this problem. And we'll discuss that later on, and then you find out the solution, how you can do so. So let's go to the for loops. The first few lines is this. Clear. For I is equal to I 1, 10, j is equal to I and. So what does the for loop here do? The for loop basically repeat the simulation, the number of lines in between with different I values. And the I will change from 1 to 10 with the incremental of 1. And that means the inner part of the line will run for 10 times. So we can copy this part into the command line, and you will see that j is equal to 1, 2, 3, 4, 5, 6, 7, 8 times 10 times the j value, because it's being assigned here as a j, and once it completes, the I here is equal to 10, right? That's basically the way how you can use the for loop. If you really want to have a better understanding it, you could use a print function. So let's say MATLAB print to screen. So basically for this is we are trying to find out how to display screen values or the result on the screen, and we put it right in the middle. So that's basically a display, I think DISP. Oh, okay, so I think that one would be better. The one here. So it's going to be sprint f. Oops. Okay, so that would be better. Let's give it a try. So name, let's say, we basically find out a template and then try to use it. So in this template, we actually got 2 strings. S. No, that's not the one. So let's move to, I think it's display X later on. Oh, okay, so that needs to be X is equal to this, and DISP X. So someone will be something in this year, right? So what we could do is that X is equal to this bit, and instead of showing something will be something in this year, we'll show this is how many times repetition. This is the D time in the loop. So the number here will reduce to 1. So we try that one here and see whether it works, and then we basically need to DISP X. Does that work? We can give it a try. DISP. Yes, okay, that works. So we can remove the output here by putting a semicolon, and instead of just changing the J, changing the 1, we display the 1, we display the J. And here you can see that after running this script, how many loops has been executed? Basically 10 times, right? And we could also check the I value here as well. So I value is D here, so then we need to put an I here. So the I is always the same as J because we defined that already. And we can run this bit again and see what's the result look like. And this is the first time in the loop. I value is 1. If you try to put that one into 2 times, then run the script again, you will expect that the J is always twice as I, right? So 2, 4, 6, 8, 10. So that's basically the loop. As you can see, the number of times the loop will run is more or less dependent on the definition of the looping argument. So currently it's 1 to 10. We could also change that to 2 every 2 points, and that will work here too. And you will find that I is 13579, not going 11 because 10 is the upper bound, and J changes accordingly. The second thing that I want to try here is a bit nested loops. So you got 4 conditions. One is from 1 to 10. The second is 1 to 5. How many times this line will be executed? The answer is 50. Because what will happen is that when you move to the I loop for the first time, I is going to be equal to 1. And then they will come to the second loop. And the second loop will be running for 5 times. And in each time, J will be 1, 2, 3, 4, 5. But the I here will always be 1. And once this loop is completed, the I will increase the value from 1 to 2. And this linear part will be executed again for 5 times, with I always being the number 2. And that will repeat until the whole loop completes. So we could make use of this tiny little bit thing to understand it better, right? So we could say X is equal to that, and this is basically I and J. So what we could do is that instead of saying this bit, so I is something, J is something. Let's call I is D, J is basically the percentage D is a format for you to display I and J, right? The other thing that we can basically put a counter here. So the counter is basically the thing to count how many times this line has been executed. The way of putting a counter is basically say Y starting from 0. And inside here, you say Y is equal to Y plus 1. And if you do that, every single time the loop has been executed, your Y will be increased by 1. And then we can check the total loop number. Total loop number is percentage D, and then we put a Y here. Right, it's now to execute this magic and see how it does it. What does it tell? And run it again. Okay, so undefined function for K. Where have we got a K? So K is here. So we need to basically say K is equal to 0 here. So, and that will solve the problem. You see, the total number of execution is 50. And the first time I is 1, J is 1. The second time run this script is I is equal to 1, J is equal to 2. And once J has passed 5, then I change to 2, and J spans from 1 to 5. And the same thing applies when I is equal to 3, 4, 5 until the loop completes. This is exactly what we call a nested loop. Usually, if you solve an ordinary differential equation like the project in modeling environmental systems, we use only one loop to solve the problem, and the I is usually associated with time. But if you actually looking at the partial differential equation where the property change not only in time but also in space, you really need to use the nested loops to solve the problem. Now let's move to using different ways to do the calculations. So the task here is to do a calculation from 1 to 100. So we add up everything all together, and the value is going to be 5050. And we can have a lot of ways to do it. So obviously for loop would be very straightforward, and that's actually the second command we give it here. So clear the value, say is equal to 0, tick and talk. So the tick and talk here is to basically calculate the time associated with running the commands. So the for loop is I is equal to 1 to 100, and say is equal to say plus I, and then that runs the whole thing. So we can run the first one here to try, and you see that basically C is equal to 5050, and the elapsed time is only 5 milliseconds. Right, that's basically the way how you run the command using using for loops. The second loop, what we try to do is basically while loop. It does almost the same way, so let's try to get the idea of it. First, clear up everything. B is equal to 0, C is equal to 0, tick, and then while B is less than 100, 1. And C is equal to C plus B. So basically C is the value that accumulates all the numbers from 1 to 100. That's basically the add up. And B is equal to B plus 1. And every single time when you run that, you add 1 to B, and every time you got the incremental. The incremental will keep going until B is less than 101. So remember, when we do the for loop, the second loop is done by adding I to our second incremental, and that's exactly the same as B is equal to B plus 1, right? Okay, now there's a question. When should we use while and when should we use for? If you actually know how many times you will execute the commands repeatedly, for loop is preferred. Whereas some other time you don't know how many loops you will go for, then it's better to use while loop. I'll give you an example. Let's say if you're using a numerical methods to converge the problem, you don't really know how many loops you need to go through. Let's say if you use a bisection methods, and the loop is more or less dependent on where the starting point is located. So if your starting point, the guessing point, is very close to your actual solution, the number of loops you will use to reach the solution is actually quite small. Whereas if you give an initial estimation far away from your destination, then the number of loops will go more than that. So in that case, as long as you don't know how many number of loops you need to use to pass the criteria, you use while loops. And if you know exactly number of repetitions or the loop you need to go through, then you can use the for loop. That's basically the idea. So we can run that again and see whether there is any difference in terms of calculation time. It's pretty much the same, a little bit more than that, right? So the result again is 5050, right? The number 3 here is actually somehow being preferred in MATLAB, is to use what we call a one-liner. So sum is an internal command, and that will summarize all the values in between, which is from 1 to 100. And this line is very neat. So one line solves the problem. That's why we call it one-liner. And we can do that again. And what you will see is that the time is actually being reduced slightly. and it does exactly the same thing. D is 5050. So if you're able to find out those internal commands to solve that, that's fantastic. But if you can only find this, that's not really a problem. And we can still use that to solve problem, because remember, your time is much more important than computer time. Even your command is relatively slow, but it's able to solve the problem, good on you. Don't worry about improve it. That's basically the later story. So if we try to go back the problem that we want to do a specific assignment. So let's say we want to change the E value to 6.5 whenever E is greater than 5 and less than 7. What we can do, what we need to do basically is to create a for loop. So for I is equal to 1 to 4, for j is equal to 1 to 4, if E I j is greater than 5, or and E is ij is less than 7. Then Eij is equal to 6.5. And. That's basically the way how you can do that. So if we run this program again, you will see that all the values greater than 5 and less than 7 will be changed down to 6.5. So let's put an E here and then get the result after the E. You will see that all the values, let's say number 8 here, that, oh sorry, this is between 5 and 7, so that means number 6 here will change to 6.5 as expected. That's basically the way how you can use for loop to solve that problem.